Well, as president of this Accademia di Torino, it is an honor and also a pleasure to welcome all of you in presence and connected for this very interesting and important conference. Let me say, in this fantastic room. For who don't know the history of Accademia, let me say a few words about it. Accademia was instituted in 1983 by the King Vittorio Amadeo III, whose portrait is on my left. But he was the king of Savoy and Piedmont. But the real founders of Accademia are three scientists, three men of culture. Among them, the most relevant is Luigi Lagrange, the famous mathematician. Usually, people thought that Lagrange is French, but he was born and lives in Torino. Well, from the beginning of the Accademia, members were about 3,000, including 45 Nobel Prizes and 3 field medals, that is, the Nobel of Mathematicians. And president of Accademia was also a president of United States, whose name is, just a moment, I have to read it, Thomas Woodward Wilson, and also a president of Italy, Luigi Einaudi, and also Napoleone Bonaparte. In fact, when the French Empire came, let me say came, in Piedmont, Napoleone wanted to be the president of Accademia. But we have a lot of significant members. Charles Darwin, Charles Babbage, and I would like the father of computer science. I am a computer scientist. And I would like to remember that the first time in the world was discussed the structure and the function of a programmable computer was in this room in 1840 by Charles Babbage. And we have in the library the original design of the machine that is called analytical machine. Also members are Champollion, the discoverer of Egyptian hieroglyphics, Galileo Ferraris, Marconi, Rita Levi di Montalcini, Ugo Foscolo, Amedeo Avogadro, a lot of scientists. Well, I would like to suggest you to look at the two globes that we have on the right and on the left. On the right, why are important? Because the globes are the second larger globes in the world. 1688. And it is curious that on the left, the globe on the left that represents the geographical Earth, the California is an island. They anticipated the thought of Trump. Okay. We have also a relevant library, more than 350,000 books. But I would like to conclude this short presentation by thank you to the organizer of the conference, of this relevant conference that deal with very important argument. And I wish you a good stay in Torino and a participation to the interest conference. Thank you.
Okay, thank you very much for your welcome message. I would like to say first thanks to the Academy of Sciences of Turin for the organization, so for all the help, and especially important, I would like to thank all the speakers for having accepted our invitations, for being here today. So, and I hope that we can foster new discussions in these very important emerging fields of crystallography. Well, I would like to say that recently the part of crystallography we are dealing with, aperiodic crystallography, is actually very important because it was originally something like a scientific curiosity that turned out to be something really, really important in order of applications and other things. So, and with all these kind of advance, I think that this kind of science, it is not only to advance it, but something like it comes with the responsibility. To communicate it effectively. And I think that this kind of meeting, so I thank you again for this possibility, it is important to try to disperse, to spread how this kind of discipline is important for all of us. Well, so as you have seen, we have a very, very rich program, including different aspects of aperiodic materials. So we'll talk about, you would say, from an historical excursions with Giovanni FERRARIS at the beginning, explaining the 2 centuries of full and lattice translations. So a lot of things which be, I think, very, very interesting. Then we'll go through an elementary introductions of aperiodic crystallography by one of the leading experts, Sander, who is present here today. And then we'll talk about some example more related to the historical fact, the loss of periodicity, the loss of the difficulty of to change the paradigm of the long-range order, but with a periodic symmetry. So we'll talk about quasi-crystals, and actually first with periodic approximant, very close in structures to quasi-crystals, and then with some particle many-body physics interacting bosons in quasi-crystals, so ultra-cold atoms, and then the discovery of quasi-crystals in nature. And finally, something tomorrow more related to the tribology of incommensurate crystalline interfaces and structures, incommensurate structures in particular kind of alloys. Then we'll visit important techniques, including electron diffraction, to study these materials. And so electron diffraction is actually one of the most important in this case, working with nanocrystals with Arianna. And then we'll move to something more related to mathematics of quasi-crystals. And finally, we'll close with something I consider a really, really breakthrough also I would like in planetary science with unusual symmetries in carbon materials, so with the diaphyte structures with Peter Nemetz. So I think that we have all the ingredients to make this event a success, and I hope that, I thank you again, and I hope you enjoy the meeting. So thank you very much for being here today. Okay, so we are perfect in time. I think that we can invite the first speaker, who is Giovanni FERRARIS. I think there is no need to presentations. He's a member of this academy. He's a very well-known crystallographer, and he will talk about something related to the 2 centuries of histories related to the lattice translations, coming from the Haüy discovery to the Shechtman discovery of quasi-crystals in 1984. So please, Giovanni.
Well, thank you for the presentation, Luca, and good afternoon to everybody, and for coming for this conference. Okay, for 200 years, people were convinced that ordered crystalline materials could exist only according to Haüy's periodic model proposed in 1784, we shall see later. That exactly 200 years later, in 1984, Shechtman showed that long-range order can exist without translational symmetry. This is something really new. We have a new class of materials, as we will hear in these days. And the aim of my talk, as already said Luca, is just to illustrate some important steps of these 200 years. The salient points of periodic crystallography founded by Haüy in 1784, and I will say also something on the first steps of aperiodic crystallography, which is the subject of this conference. Actually, periodicity was known to people studying crystals even before Haüy. Just a pair of examples. Observing honeycombs, since the 16th century, famous scientists realized that closest packing of submicroscopic particles could be a key to explain properties of the crystals, in particular the morphology of crystals. Now, just 2 examples of famous scientists. One is Italian, he was involved in mechanics. Gerolamo Cardano, in 1550, explained the 6-fold morphology of quartz, just supposing that the crystal structure, let's say, was based on what were called particles at that time, on particles probably hexagonal like in the honeycomb we have seen before. The other scientist I remember is even more famous, is Kepler, who wrote a booklet about the morphology of snowflakes, and they used this booklet as Christmas present for friends. This is translated in several, I don't know how many languages. This is the original one. Didn't have a 6 angular, of course, at that time they used Latin. Okay, also Kepler imagined that the hexagonal symmetry of the snowflakes is based on the closest packing of spheres. Yes, I say nothing really new. Mine is an historical excursus. An important point is the discovery of birefringence. I think that it is the first anisotropic physical property discovered. I think it is this one. It was discovered in 1669 by Erasmus Bartholinus, and the explanation came a few years later by a very famous scientist, Christian Huygens, in his Traité de la Lumière, Treatise of Light. And in this case, he supposed that the crystal structure of calcite is based on a closest packing of ellipsoids. That means that the crystal structure is anisotropic, because spheres are isotropic, ellipses are anisotropic. And that means that the light traveling through the crystal experience different velocities in different directions. Okay? That causes the splitting of the incoming ray of lights, and we have the so-called birefringence. Well, before I said particles, they use particles. And they began to use, as scientists, a more familiar word, integral molecule, later. And Haüy was the first one to use it in a theory of our interest. Well, in 1766, the French chemist Macquer, who was being one of the first members of this academy, okay, defined the integral molecule as the smallest aggregation of simple molecules, atoms, that maintains the chemical composition of a compound. Nowadays, we can identify this integral molecule with the unit cell of crystals. Yes, in modern terms, now instead of integral molecule, we say molecule, and instead of simple molecule, we say atom. Okay. Now, Haüy has to be considered the father of modern crystallography. He was a professor in Paris, Jardin du Roi, now the Jardin des Plantes. And in 1784, he published his theory proposing that the crystal structure is based on a periodic repetition of the integrant molecule. Okay? Nowadays we say on the periodic repetition of the unit cell. These are the original drawing by Haüy. And also atoms were supposed to be polyhedral. Actually, Haüy was aware that this was a very rough representation, but he just wrote literally, yes, he said, but chemists don't know more so far. We were more than 2 centuries ago. And these are sections of the integral molecules with inside the atoms. Anyway, theory proposed by Haüy has been successful, and including periodicity. Even if it's not perfect, for example, it could explain hemihedral crystals, we shall return on that. And very important research has been done around periodic materials. Research concerning symmetry of crystal morphology and crystal structure, concerning the nature of atoms and molecules, because the crystal science, at the beginning, was the science of the structure, of the atomic structure of matter, and also about the natural configuration of chemical bonds. Let's remember some of these important steps. First of all, concerning symmetry. In 1830, Hessel discovered the 32-point groups. The 32-point groups are the possible symmetry of crystals, the macroscopic symmetry of crystals. And 20 years later, Bravais discovered the 14 lattice, which are also known as Bravais lattice. Okay. And the 14 lattice are the 14 different types of periodicity for mathematical points. But, because nowadays, unfortunately, a lot of people, more and more, they use lattice as a synonym of crystal structure. No, lattice is a mathematical concept, okay? And only at the end of the 19th century, in 1892, the 230 space group which described the possible symmetries of crystal structures. And so we have the symmetry of crystal, the symmetry of the mathematical array, the lattice, and the symmetry of the crystal structures. And they discussed a lot anyway. It took about 30 or 20 years to define. But finally, two different scientists, the Russian Fedorov and the German Schöfris, published in the same year 2 different papers describing the 230 space groups. An important role in the development of crystallography, but not only of crystallography, of the science, the structure of matter, are isomorphous series. And with isomorphous series, we can see also, let's say, a realistic description of atoms. In particular, it is supposed that in a isomorphous series there is a substitution atom for atom. Well, I would like to remember here that Berzelius, of course, is considered one of the most important chemists we had in the past. In 1828, Berzelius calculated the first modern atomic weights, observing that if AX and BX are isomorphous compounds, it holds the following relation. The ratio between the atomic weight of A and the atomic weight of B is equal to the ratio of the weight of A combined with X and the weight of B combined with X. That means that with a macroscopic measure, the weight of matter which combined, we can have the ratio. Of course, the atomic weights are relative also nowadays. Usually, we can say that hydrogen is 1 or oxygen is 16. And also Mendeleev, to define this periodic table, used the isomorphic series. Actually, his graduation thesis was on isomorphic series. Here it is shown on the left the periodic table published by Berzelius in 1828. On the right side, it is just still a rough representation of the periodic table, because Mendeleev just sent to France one page written in French reporting this table, and this table has been published on the Accademia, just one page. One can see that there are still several question marks, and some of the question marks will be solved, taking into account that if elements A and B form isomorphous compounds, it means that A and B have the same chemical properties. Now, some pioneering hypotheses on the periodic crystal structure. As early as 1824, this is really astonishing, Fresnel discovered the optical activity, but he also imagined how could happen this phenomenon. He writes, the optical activity may result from a helicoidal arrangement of the molecules in the medium, which would offer inverse properties according to whether these helices are either right-handed or left-handed. And 24 years later, Pasteur, before to become a biochemist or something like that, but he was a crystallographer, and several artists at that time, because crystals were one of the objects offering more way of investigation. And Pasteur adopted Fresnel hypothesis and improved also the Fresnel hypothesis in his research on enantiomorphic compounds. For example, he studied, these are left and right crystals of tartaric acid and left and right crystals of quartz. And also, this is important because tartaric acid is a molecular compound, and there is optical activity in crystals and in solution because molecules are optically active. Instead, quartz, this was noted by Pasteur, the quartz is optically active as crystal, but fused, I don't say in solution, fused quartz is not optically active because there are no molecules in quartz. No? There is silicon and oxygen. Well, I already mentioned that Haüy's theory couldn't explain hemihedral crystals because the model, Haüy's model is centrosymmetric, and so. In 1844, Gabriel de la Fosse proposed the model. I show you the model for the mineral boracite, supposing that the crystal structure is based on a packing of tetrahedra. And for the first time, there are voids because in Haüy model there are no voids in the crystal structure, and is not centrosymmetric. Okay, and so also this problem that couldn't be explained by Haüy theory was explained. And now we are at the eve of the discovery of X-ray diffraction at the end of the 19th century. And Paul Groth proposed an interpretation of the crystal structures, nowadays we know, which has been very useful for the first determination of crystal structure, because he pointed out that the crystal structure consists of interpenetrating Bravais lattices, each one accounting for the spatial distribution of an atomic species. So for example, sodium chloride, no? There are two interpenetrating lattices, and each lattice is occupied, one by sodium and the other one by chlorine or chloride. Well, 1912, everybody, of course, has seen that, no? The students of Haüy, actually were not, the students in the department of Haüy, no? Sent X-rays on crystals and obtained something shown just here below. This is the first diffraction pattern, okay? It was something completely new, okay? Because if we send a beam of light through the matter, no, it is not diffracted. And the beam is X-rays, okay, well, Haüy, he already had published an explanation of diffraction in 2 dimensions, and so he thought, yes, I can extend to 3 dimensions. Actually, it's not completely exact, the derivation by Haüy, but anyway, it works. And he could explain the diffraction on the basis that the crystal structure was periodic. In fact, here we can see now the equation connected the interplanar spacing D, which is related to the periodicity, the diffraction angle theta, and the wavelengths. And also, only 1 year, in 1913, Bragg father and Bragg son published the first crystal structure of elements, in particular that of diamond. How could they succeed? Having in mind was said Paul Groth, but also they just connected the direction of diffraction, so the angle theta with the interplanar spacing, and they measured the intensity of the diffracted rays, and were able to see that the most intense diffracted rays were those diffracted by planes were situated atoms and so on. Anyway, I just do an excursus. Well, we can conclude that X-rays are able to detect periodicity, okay, and are also able to show atoms. It is well known because it was not yet clear, not everybody, every chemist and physicist was convinced that there were molecules and atoms at that time, okay? And a lot of people said in the structure of sodium chloride, yes, but where is the molecule? No molecule, it's impossible. Okay, yes. And so it was seen, it was touched by hand, that there are compounds based on molecules and compounds based on ions or metallic compounds and so on. It is only after the discovery of X-ray diffraction. Well, now the last few slides are dedicated to the first steps towards the aperiodic crystals. Actually, already in the middle of the 19th century, the problem was discussed because of mistakes in measurements, but sometimes also the mistakes. Well, the invention of the reflective goniometer in 1809 allowed to measure the dihedral angles of a large number of crystals, even of millimetric dimensions. Even now, this instrument is used. Before, instead, was used the contact goniometer, and crystals had to be of centimetric dimensions. Yes, but the reflective goniometer has a drawback, that the light can be reflected also by defects of the crystal, defects like striation, like microfractures and so. And so if somebody measures the reflection of the faces of the crystals, and after he tries to index all the reflections, he finds that not all the reflections can be indexed, because some reflections do not belong to the crystals. Anyway, now we know these things, but not at that time. For example, Scacchi, who was professor of mineralogy at Naples University, supposed that the irrationality of the index was due to the repetition of crystal forms with a slightly different dihedral angles. He was thinking just the many small faces close each other, okay? And he called polyhedrid this hypothetic. Okay. Yes, I said, sorry. Okay. No. Who am I? Oh, yes. Sorry. Here you are. Okay. Well, the problem was solved about 50 years later. No? In particular, at the beginning of the last century, Smith and Goldsmith measured calaverite, which has a lot of small faces, and the selected reflection that were not originated by macrophages and so. Okay, and anyway, they actually, in this case, were not able to index all the reflections based on a unique parametric ratio. No? they had to use more parametric ratio. Or if you like, they had to index some refractions with not integer Miller indices. Where in 1936, they published the diffraction pattern of Calaverite, and but only in 1964, with the solution of the sodium carbonate structures, it was also published, let's say, a model to explain this strange. In fact, in the pattern of Calaverite and sodium carbonate, there are strong reflections and weak reflections, the so-called satellite reflections. And the explanation has been that on the basic periodicity, which give rise to the stronger spots, there are perturbations, modulations over important, okay? And so in this way, mathematically, they could explain that the modulations or perturbations could generate the weak reflections. But this is, well, and we are at the last two slides. In 1974, Penrose, a mathematician, I think, proposed a two-dimensional periodic ordered tiling based on two rhombi with obtuse angles measuring 108 degrees and 144 degrees. Well, with these two rhombi, it is possible to fill the plane, okay? But what happens? That this tiling is not periodic and shows symmetry 5, which is not compatible with periodicity, okay? And I don't know how long we're able to discuss this, because exactly 10 years ago, the experimental evidence that we can get diffraction from non-periodic materials was published exactly 200 years after the publication of Haüy periodic. Sometimes, the history plays with this thing. Exactly 200 years later, Shechtman and co-workers published the electron diffraction pattern of an aluminum manganese alloy. Here there is diffraction, and the symmetry of this pattern is icosahedral, which is inconsistent with three-dimensional periodicity. This is just a projection, but okay. And however, long-range order is maintained. Yes, mathematicians tell us that if we obtain sharp diffraction spots, it means that there is order, okay? Well, order is maintained, but there is again rotational symmetry 5 and 10, okay? And now I have finished my talk. I leave to the other colleagues to explain more. Okay, thank you very much.
So thank you very much, Giovanni, for this very interesting excursus. The session is open for questions. Do you have questions, comments?
Well, everybody seems happy.
Yes. I wish to thank again for the importance of the historical reconstruction. So these things sometimes are easily forgotten. So thank you again.
Thank you.
Okay, so Giovanni talked also about Calaverite, which is, I don't know if you know, it is a gold telluride. Okay, it is actually very important for the extractions of gold. And structurally is a one-dimensional incommensurate modulated structures. And the best way to introduce what these kind of structures are is to do with the best speaker I can imagine for this kind of introduction, of elementary introductions to aperiodic crystallography. Is Professor Sander van SMAALEN. Is retired professor of crystallography at the University of Bayreuth in Germany. So please, Sander.
Thank you very much. Thank you very much for the invitation to be here in this impressive room. And I would like to give a brief introduction to the crystallography of aperiodic crystals, specifically of the modulated crystals, so I will not say much about quasi-crystals. Interesting.
Try to move with the arrow or the keyboard. Okay.
Yeah. So what I will do is introduce the crystallography of modulated crystals in a more general way, and in the last part of my talk I will present to you our recent results on europium aluminum 4 charge density wave compound. And on that part, I would like to thank my collaborators, and in particular for the crystallography part, Surya, who is PhD student with me, and Sitaram Ramakrishnan, who did his PhD several years ago with me, and now is in Grenoble. So what about incommensurately modulated structures? For those of you who have done physics, it's very easy to think about it as a frozen phonon. It's a wave, so here we have in the dashed lines a lattice, just 2 dimensions out of 3 dimensions, and the circles represent atoms, and we have 1 atom at the origin of the lattice, on the lattice point, and you can see most atoms are displaced to the right or to the left or to the up or to the down, meaning on the left side a longitudinal wave, and on the right side one of the 2 transverse components of this wave. And the wave is schematically given below the picture, and what the recipe you need to do is that you read of the amplitude of the wave at the lattice position and then shift away this atom by this amount to the right, or on the left side by this amount to the up. And in that way you create a crystal structure which is not periodic anymore, in particular not by this dashed line, and also not by a supercell, because you can see the wavelength just misses 3 basic translations of the dashed lines. Well, such a wave is described preferably by a wave vector Q, which in this case has some incommensurate, irrational, or unrestricted component along the A2 star or B star basis vector of the dashed lattice, and one can also, with the length of this modulation wave vector, we can associate with 1 over the wavelength of the wave, which is not related to A2 or B translation. So now I take this part. We just consider 1 dimension out of our 3-dimensional crystal. These 2 pictures were 2 dimensions, and draw that together with the wave. Our recipe is again here. So we read of the value of the wave at the basic position or lattice periodic position, and then shift the atom in physical space by this amount to the right, or when the amplitude is negative, we shift it to the left. This is the same Q vector, and the position, there is a basic structure or lattice periodic position, which is when the modulation is 0, given by x bar, and it's an integer for the unit cell number plus some position in the unit cell. And then we have the real position when we shift by different amounts in different unit cells, and that is this wave function. And a wave function, as the word says, whether it's phonons or modulations, is a function of Q scalar product with the basic position. That is the argument of a wave function. and here it's written out. And I already added this t parameter, which is kind of starting phase of the wave, which in some sense is irrelevant because the wave is incommensurate, but in other sense I will show is very helpful in analyzing these structures. But for now we can choose t equals 0, for example. The description developed by de Wolf, Janner and Janssen of the so-called superspace description can be derived in different ways. I've now chosen to take physical space. The circles have moved or transformed into dots, representing the atoms, and I think you can see that is not a periodic arrangement. And then in superspace we make a fourth or additional dimension perpendicular to physical space, and we make a periodicity along this superspace which is equal to the wavelength. We call it AS4, S for superspace and 4 for fourth coordinate axis. The first three are physical space, of which I always only draw one because I cannot do this four-dimensional perspective drawings. And then there is this AS2, I think I need once more, vector, which is kind of arbitrarily chosen, but that's not true. It's chosen to make an angle with physical space such that we have sigma 2 ratio to 1 minus sigma 2. So we split this length fourth axis in sigma 2 and 1 minus sigma 2. And it's not on the sheet, but I showed you on 2 sheets already. This sigma 2 is the component of the modulation wave vector. And if it's a rational number, it's of the incommensurate structure. So that is the direction we have chosen, and it are the basis translations now of four-dimensional space. And now we can translate atoms to the first unit cell in four-dimensional space. And you will see that they all ends up somewhere on this modulation wave. Or the other way said, which is maybe better, they shifted positions, construct the modulation wave from the observed positions in physical space. And you can see if we do that for all atoms, then we densely fill this modulation wave is translated points. And we have constructed this modulation wave, this one period of the modulation wave of the atom. So to summarize that, the superspace equivalent of a point atom, as we often use, is not a point anymore, it's a string, here given in red, of 1 unit cell long and on the average perpendicular to physical space, meaning on the average along the fourth axis. And then we apply again all these translations, so it's easy. We go up with the second superspace translation, we get all these strings, and then we go down with AS4, and then we fill up all of space with atoms, and now we see that an atomic string extends infinitely long and is periodic along the fourth axis. And the atomic positions, very important, now follow as the intersection of the wavy string with physical space. So that are all these real modulated positions you find here. Yeah, just a small excursion. Composite crystals, this is a misfit layer compound, and the left picture you say, okay, yeah, that is a periodic crystal because I see a lattice translation B to the right and a lattice translation C to the up, and we have here 1 unit cell. If we turn around 90 degrees, then you say, okay, it's not so good because the third translation, which you don't see in the left picture now, is from left to right, the A, and you see the niobium of tantalum disulfide has a short translation, and the lanthanum sulfide has a longer translation. And if we make several unit cells, you see again 3 unit cells of the tantalum disulfide do not match 2 unit cells of the lanthanum sulfide, and actually the ratio is an irrational number. I won't go in any more detail on these composite crystals, but they are also described by this superspace theory, and they are also famous in minerals. Again, this is synthetic cylindrite structure solved by Markovici and Petricek and co-workers. And here you see the modulation wave much more strong than I've shown before. So that is modulated structure with the superspace model of these wavy strings perpendicular to physical space. Now let's go to the diffraction before we complete this analysis of the modulated structure. And diffraction and symmetry, so one can say, I don't care about symmetry. So why should I care about it? And the answer is very clear: to avoid correlation between parameters. And that's everywhere. So if you have thermal expansion, if it's equal along 2 directions of a cubic symmetric crystal, then it's equal by symmetry, and it doesn't make sense to try to accurately determine the thermal expansion along the A-axis and the thermal expansion along the B-axis, because they must be equal. And in most experimental technique, they suffer from the problem, if you ignore this equalness, that you have correlated parameters in your analysis, and the analysis doesn't work. And that is specifically and particularly so by crystal structure analysis against X-ray diffraction. If you forget about the symmetry, you cannot solve your structure. It's also very important for certain physical properties, as I've indicated here. Inversion center as part of the symmetry or not allows us to find out beforehand whether a crystal is a candidate crystal for nonlinear optics, or with inversion it's not. And that is all summarized in Neumann's principle, which says that the symmetry of a physical property of a material includes the point symmetry of the crystal structure, but it also may be more. And one way where it's more is the Lawes symmetry of X-ray diffraction patterns, where X-ray diffraction with some small difficulties adds inversion center to the symmetry group of your crystal. So these aperiodic crystals, they don't have translational symmetry, and that also means, in some sense, they do not have rotational symmetry. Maybe there might be one point in all of infinite space where this rotational symmetry applies, but because of the lack of translational symmetry, it's never repeated. And it would be a big coincidence if the 1 centimeter crystal we select would contain this point out of all of infinity. So it's safe to say no translational symmetry, then there is no rotational symmetry of the crystal structure. Nevertheless, we now know that aperiodic crystal is an ordered state of matter, most effectively pronounced by diffraction, where we see sharp Bragg reflections for the aperiodic crystal as well as for the crystal with translational symmetry, but they cannot be indexed with 3 integer indices. So long-range order is reflected by sharp Bragg reflections, and the other way around also, sharp Bragg reflections you have when there is long-range order. As it happens to be, this diffraction pattern does have a point symmetry. The diffraction pattern exists in physical space, in our space, in 3-dimensional space, so it's a 3-dimensional point group. And there it's similar to periodic crystals, because also for periodic crystals in reciprocal space, the diffraction space, there isn't any translational symmetry anymore. We can index with 3 integers, but if we consider the intensities of the Bragg reflections, there is nothing to translate, and we observe a real point symmetry about the origin. So this 3-dimensional point group, or point symmetry, we want to assign to the crystal structure of an aperiodic crystal, and that's called superspace groups, as have been developed by de Wolf, Janner, and Janssen. Well, the first part, that is these 3-dimensional point groups, that has been solved, I guess, a long time ago by mathematicians. And Giovanni already said there are 32 crystallographic point groups, which can then also, apart from periodic crystals, be the fundament for describing the symmetry of aperiodic, so modulated and composite crystals. Then, if we do not insist on long-range order, we have local order. For example, with proteins, we can have the 7-fold arrangement of 7 equal protein molecules. Very nice. This is a picture taken from the protein data bank, so experimental crystal structure of a protein structure containing these 7 copies in a 7-fold order. And the mathematicians tells us there are, starting with 4 over MMM and 6 over MMM, there are actually n over MMM, an infinite number of these groups based on the highest symmetry rotation axis, 5-fold, 7-fold, 8-fold, 9-fold, 200-fold, whatever you like, and that's all. And then we have special groups. On the left side, a special group is, for example, the cubic symmetry group, which combines 4-fold and 3-fold axis, whereas n over MMM has only 1 n-fold axis and quite a few 2-fold axis, but no combinations. And the other non-crystallographic combination is the icosahedral group, which contains 5-fold and 3-fold axis, and which is found also said by Giovanni for quasi-crystals, and also the other n over MMM based point groups can be the symmetry of quasi-crystals, and several have been found. But there are no more point groups to consider, and for the superspace groups it really is only the crystallographic point groups that we need. And otherwise we are with quasi-crystals. So this is experimental diffraction pattern. That means reconstructed reciprocal layer from the actual measured frames. This is a periodic structure, and if you cool down this morpholinium fluoroberylate, as done by Laila Nohiniat, then at 130 Kelvin you see additional reflections, which are called the satellite reflections, and which cannot be indexed with 4 integer indices, but we can index the neighboring main reflection, which are the ones which exist solely at higher temperature. They remain here, and then we can describe these extra spots as a distance q away from such a main Bragg reflection. And this distance q is valid everywhere. Sometimes there is missing, that's allowed, or invisible intensity, or not measured intensity, but there are no other positions, and in particular, wherever you do it, you need the same q, which here is 0.4216 A star. Mathematically, the same is we can also then have minus q, which explains why we have 2 of these satellites close by. One is plus q from the left, and the other is minus q from the right. And this is schematically a similar idea, where we have A4 star or q, that are alternative ways to denote q, or A4 star is this irrational fraction times A2 star, as we had before. And here it's chosen in such a way that the first and third component of Q are 0. And you can see here how easily it gets complicated. Such a first-order satellites, 1 times Q, can be close by a second-order satellite minus 2 times Q coming from the other main reflection. But if you forget about this indexing and just look here, you see, okay, I have 4 additional spots, how to index them, and it's not always immediately obvious. Another important thing is we index with 4 integers. That is the crucial part. But of course, we can also describe all points in space with 3 indices with respect to A1 star, A2 star, A3 star, except that we have this complicated irrational component of an integer plus this m in front of Q times the irrational number of Q. Yeah, and superspace is made in reciprocal space when we take our physical space with the main reflections, nothing changes. Our superspace is perpendicular to physical space, and the superspace lattice makes a strange angle, which is complementary to the angle of the A2 axis. Here it's A2 star, and it is Q in physical space, and B star or A S4 star in the additional dimension. And you see nicely that the satellite reflections are considered as projections from reciprocal lattice points in 4-dimensional space, whereas the line m equal 1 projects on Q, and the line m equal minus 1 projects on minus Q. And that's the reciprocal unit cell in superspace. The m equal 2 projects on a second-order satellite to Q, which I didn't draw here, because then it gets too full. So it's this projection or relation between 4 indices in physical space with main reflections and satellites, and reciprocal 4-dimensional reciprocal lattice in 4-dimensional space. And that brings us to the central scheme of the superspace description by Janne Jansen and de Wolf. At the bottom half we have physical space with an electron density governed by all the atoms at their positions. Then we can do a Fourier transform in physical space, and we get the structure vectors. And the square of the structure vector is the intensity of the Bragg reflection. And in superspace, we have a 4-dimensional generalized electron density, and we can do a Fourier transform, and we get also the structure vectors. And that are the same structure vectors as here. We have a projection of 4 indices in 4-dimensional space to 4 indices in physical space. And the big thing which Janne Jansen and de Wolf succeeded in is doing the inverse of this projection operator, which in general should not be possible, but because we can do this indexing of Bragg reflection, we can do the inverse projection. And in physical space, it's this generalized density, and we take an intersection as physical space to get the electron density, which we really want. So here for erbium iridium silicide modulated compound, you see here an iridium atom at its position x1, x2, and the x3 or z coordinate is here, and the force coordinate is vertical, now starting 0 at the bottom and 1 at the top. So the periodicity is 1, it counts the periodicity, so 1 means 1 wavelength, and then this figure continues periodically. And what you now can do is take physical space at t equals 0 and then shift it by increasing t until t equals 1. There we are. And all these intermediate intersections give us the same physical space, but phase shifted. And the maximum trace we trace out with all these sections gives us the modulation function. Here also once more in coordinates. So this sodium atom, that's of course a almost spherical symmetric electron density, high in the middle and low farther away from the position. So that is translated modulation wave. Again, the t equals 0 section, and we see, okay, we must have a shifted atom here, and we can shift it back where we did before, and we get a dense filling of the modulation wave. Yeah, one issue which sometimes come up and actually is quite important, is it a commensurate modulation like a 5-fold supercell, or is it really incommensurate with an irrational number for this sigma, for this Q vector? And I like to illustrate the problem with chromium oxychloride. It's orthorhombic, you can see on the left, and under pressure it becomes all wavy. And with the black line I highlighted the wave, maybe you can estimate some wavelength. And the reason is that these chlorine atoms at high pressure fill up better this van der Waals gap when they are modulated. Yeah, and this modulation wave is pressure dependent. Both the amplitude, which I do not consider here, is pressure dependent, and the wavelengths or Q vector. So here going from 15 to 58 gigapascal. And as you can see, at high pressure, it first reaches this point, and then pressure is released. It stays exactly at 1/3, so one might, or one is inclined to believe here the modulation is commensurate 1/3, 3-fold supercell. In between, here on increasing and decreasing pressure for filled and open circles, it passes many values, so one is inclined to say, yes, that is incommensurate, because there is no fixed value to a specific rational number. But at lower pressures, 15 to 25, it's about 2.7. Maybe this is an experimental error, the deviation. Maybe it is incommensurate. Maybe. And that's very difficult to determine. And one reason it's very difficult is that with this sigma is 2/7, and maybe I should point out, 2/7, 0, 1/2, I need 14 steps to be back at 3 integer numbers. And that means that if it is 2/7, it's commensurate, but we have 14 of these satellites and also 14 unit cells to make a supercell, to make it periodic again. So here is how we would index 1Q, 2Q, 3Q, 7Q. We are halfway. That's this half, which doubles everything, and it reaches -7Q from the other sides. We can also consider all these superlattice spots in one reciprocal unit cell of the basic structure, and here is the M index. So the 1 is here, that's this one, and the 2 is here, that is this one, and so on. And you see they are nicely separated by 1/7. Yeah, and the problem is displayed here. This is displacement modulation. I forgot which atom. Oh no, it's written here, chromium atom, in the Z direction. Okay, we just take one. And the line here is for the assumption of an incommensurate modulation. Then we have a continuous modulation, and if we take a point on the line, we find some t-value where it's realized. So it's there. If it's commensurate, we need on this line 14 points. So we can have 14 black points where we start with t is 0, or we can have 14 open points where we start with t equal 1/28. We can also do other choices, but these are the two special choices. Suddenly we have a 14-fold supercell of orthorhombic PCMN symmetry, or a 14-fold supercell of orthorhombic PMMN symmetry, or we have a incommensurate modulation with orthorhombic superspace group. And you can imagine, if you now need to compute your structure factor, that just using the black dots or just using the white dots, you already make a very good Riemann approximation to your integral over this modulation wave. So in our structural analysis, sometimes one sees a difference, one fits better than the other, but quite often, especially in such cases, it is very difficult to distinguish the two. Also from a more physical, philosophical point of view, it's maybe important, but not so easy, because one can imagine if we have the black dots, it's actually a similar structure than if we have the white dots. We have a large displacement here, and a smaller or a negative displacement here, and 0 here. So that is all very similar, or one can even go as far here. If it's commensurate, it can be 0 or 1 over 28. But if to move from 0 to 1 over 28, I don't need more than kT of energy. It doesn't make sense. There is no difference between the two. So eventually, the energy differences get too small to distinguish a high-order commensurate modulation from a true irrational or incommensurate modulation. Yeah, now this...
3 minutes.
Oh, you gave me 45.
Oh, sorry, okay, you can go ahead. So, sorry, it is written here. Sorry.
Yeah. I can stop here, but...
No.
So this T value, T plots, more than the shift of an atom, we are maybe interested in interatomic distances, and here it's indicated if we have a certain T, then we find this distance in our original physical space. Or the other way around, this distance in original physical space we find here at a different T in the first unit cell of superspace. So we can again shift T, and instead of a modulation wave, we now plot the distance. Also looks like a sinus, it's not. It's a bit different shape, difference of two sinuses. And we can do that for this iridium atom I've shown to you before. This is the position of the iridium atom. And we can do that as a function of the argument, x4, but that's not what we want. We do it as a function of t. And you can see it just shifts along the horizontal axis because we subtract a certain amount from the x4. But this certain amount depends on the atom we have, so we subtract different amounts q dot x for different atoms. And that's exactly what we need with a function of t. We get everything in the same physical space. This is a close-by silicon atom, and you see they modulate nearly in phase in such a way that the distance doesn't vary too much. And that's what you can learn, for example, from such a T-plot. So now I come to my last part, if I'm allowed. And that is our recent results on charged density wave compounds, europium aluminum 4, strontium aluminum 4. So this is the europium aluminum 4 compound electrical resistivity as a function of temperature by Nakamura and Shimomura. And you can see it's also very anisotropic along A. There is a small anomaly here, but along C there is a strong anomaly indicating charge-density wave transition, sudden upturn of the resistivity, and here it gets complicated. Shimomura found 4 successive magnetic transitions to different types of anti-ferromagnetic order. The charge-density wave transition is 145 Kelvin, so much higher. But one can imagine the symmetry, which we arrive here at below 145, is the starting point for the symmetry of the magnetic phases, so quite important. This is the basic structure, I4 over MMM. Symmetry with lattice parameters given here, rather small unit cell, europium atoms at the corners and at the eye center, and then aluminum 1 and aluminum 2 atoms. I think this is aluminum 2, yeah, and aluminum 1 atoms in between. For tetragonal I4 over MMM, we can also do F4 over MMM. That's just a different setting by taking the diagonals. So now it's, instead of 4, it's 6 angstrom unit cell. That is this diagonal and this diagonal. And otherwise the structure is the same. It's a different setting. That means F4 over MMM you don't find in the international tables, because it's not a different group. The structure is quite simple. Europium, fixed position, aluminum 1, fixed position, aluminum 2, 1 free parameter. And that's our diffraction. On the left, our earlier diffraction with only first order satellites, and then we made beta crystals. And you can see here second order satellites. So we got a data set with second order satellites. Yeah, so this problem with I and F is that if we go from the eye center and we keep these mirror planes and do away with the fourfold axis, we get IMMM orthorhombic. And if we keep the other set of mirror planes, the diagonal mirror planes of I4 over MMM, we get FMMM. And here IMMM and FMMM orthorhombic are essentially different. As tetragonal, it's different settings, but as orthorhombic, it's different space groups. And yeah, the I4 over M turned out not to work well, because you can see these two mirror planes generate two different mirror planes which have a different symbol here. One is mirror S, and the other is mirror 0. Here the two mirrors are the same by fourfold rotation, so they are both S or both 0. And that turned out not to give a good structure, so the S is the intrinsic translational component along the force axis. Don't need to know in detail, just that 0, S and Q are different. S is for 1/2, Q is for 1/4. And then we can take subgroups of these groups and we get a non-central symmetric I222 or F222. Yeah, just a few numbers to illustrate how difficult it is to decide on the correct symmetry. This is the basic structure, refined against main reflections, and that gives these residuals, which especially the 1.8% is quite good for a structure refinement. Then one special is the same number of parameters. That means this small structure with 3 atoms remains the same even if I go to the lowest orthorhombic symmetry. So the basic structure remains tetragonal. And the deviation, as I will show to you, there is a deviation, is entirely due to the modulation wave. And the basic structure here, this is due to data processing. We don't know how to improve, but all R values are small and indicate an excellent fit. And no reason, well, this actually is the same tetragonal basic structure. Then we add first harmonic displacement, then we have also satellites. And at first instance, especially I422 looks good. This 20% is not so good. But there are two problems. One problem is the main reflections have a higher R value than in the basic structure. So when I add the modulation, I describe these main reflections less good, and that is not good. Because by adding more realistic structure model, I should improve the fit to the experimental data and not make it worse. So that is one problem, especially also here, but for all three. And the second order satellites, they are fitted not so well here, but the main problem, that's why I put a star, is that they are calculated way too strong as compared to the experimental values. And if it's noise, then we should have equal amount stronger and equal amount weaker calculated than experimental. And that means there is something missing from the model. One can add second harmonic displacements, then doesn't help, they refine to 0 because they would make more intensity here, and there is already too much, and what helps is second harmonic modulation. So we see, here we go down, this is not satisfactory, but especially FMMM now appears good. This is good, that's not so terribly good, but many structures have been published. Then came this paper by Niemeyer and co-workers, convergent beam electron diffraction, and they had some argumentation of a global centrosymmetric structure and point symmetry of the structure, which are not appropriate for this incommensurate structure because there is no difference between global and whatever structure. There is a crystal structure which is incommensurately modulated, and there is no point symmetry. Nevertheless, in convergent beam electron diffraction, you see the point symmetry, and they came up with non-centrosymmetric, so we tried non-centrosymmetric. First, this picture. This is my would-be twofold rotations, and it's maybe not all that easy to see. Here the green is on top and the blue on the back. Here the blue is on top and the green is on the back, so that seems to match with a twofold rotation about this axis, but there are other parts. So if we want to relate this one with that one, or at the bottom it's even stronger. We see here a green dot with the blue perfectly behind, and here we see the blue on top, but you can also see the green behind. So different displacement in the B direction here and there, and that's as it must be. You can also see this atom is at the lattice point. This atom is clearly shifted along the A axis. So no point symmetry. Nevertheless, convergent beam electron diffraction sees point symmetry if you just look at the experiment. And we tried the non-centrosymmetric groups. This is what I showed before. And now we removed this second harmonic modulation of temperature parameters, and we get something which is a clear improvement of here, but still with two problems, higher than the basic structure, and this problem is calculated too strongly, and that's then repaired by the second harmonic temperature factor modulation. This is good, and that is suddenly much better than the basic structure of 1.81. And the second harmonic ADP modulation was published quite a few years ago, is an indication that this compound has phase-on disorder or some other way. You might hear about more with relation to quasicrystals. So that's the modulation functions. You can see aluminum 1 and A and B. Along A and B, they are equal here, and here they are strong along A and weak along B. You can see that here all atoms move coherently, more or less, and here the amplitude is much smaller, but you see the blue ones go left to right and make a strongly varying distance to the green ones. And that is for us then the source of the charge density wave. So I guess I will skip that, and we came up with this kind of diagram that for this particular structure type, the C over A axis needed between 2.5 and 2.58 angstrom relation, in order to find a charge density wave. And then my conclusions, that the superspace model for incommensurately modulated crystals, but also more general for aperiodic crystals, reveals the hidden translational and rotational symmetries. T-plots can be used to do the crystal chemical analysis by looking at distances, but also angles, magnetic moments, whatever. And for europium aluminum 4 charge density wave, we have found its incommensurate, non-centrosymmetric orthorhombic charge density wave, while the structure remains tetragonal. Thank you.
Thank you very much, Sander. And the session is open for questions. You have questions, comments? Please, Marta.
So maybe you explained this and I didn't get it, but how systematic extinctions apply to satellite reflections the same way as normal reflection?
So your question is reflection conditions, whether they apply to aperiodic or to modulated crystals. The answer is yes. It is a straightforward extension, but not all that simple. For example, what I've shown you in one example is a Q vector of irrational 0, 1/2. And this 1/2 component is fixed by symmetry and is actually an indication that there is a 4-dimensional centered lattice. So you need to go the whole analysis by introducing centered lattices for the 4-dimensional superspace groups, corresponding Bravais classes, and then yes, you have the conditions on the HKLM indices.
Okay, thank you.
Okay, so all the superspace groups are now tabulated with all the reflections conditions. So
they are now tabulated up to dimension 3, 3 plus 3.
Well, so other questions, comments? Well, so we are perfect in time. We have a break now. And so I thank you again, Sander, to be here, and thanks for your talk.
Thank you.
And for people attending online, we have a break of a half an hour, and we'll restart at 4:45. So see you.